So if you can't get in or you're not able to join us on Zoom, you can watch it on Facebook. Finally, we will continue to do this is recorded and will go onto our YouTube channel. So probably this weekend, all 3 of our sessions will be on YouTube so that you can go back and watch those. We will also be sending out in one email for all 3 sessions, we'll be sending out the step-by-step instructions for all of the experiments that you've seen. And just a quick reminder too, if you haven't seen the supply list, it is also still available on our website where you registered. So once again, we welcome you, and we'll get ready to get started here. So today I'm going to introduce Dr. Janet Asper. She received her Bachelor of Science in Biochemistry from Ohio University and her PhD in Chemistry from the University of Pittsburgh. She joined the faculty of UMW in 2005 and teaches organic chemistry, general chemistry, NMR spectroscopy, and a first-year seminar titled Chemistry and War. She's active in the American Chemical Society at the local and national levels, serving as counselor for the Virginia local section. She has spent 7 years on the ACS Committee for Community Activities, developing outreach materials that are used internationally for National Chemistry Week and Chemists Celebrate Earth Week. Her research interests include superabsorbent polymers, microplastic pollutants, development of new methods to synthesize, alkyl guanidine, I'm sure that's not right, molecules, the history of chemistry, and the use of NMR spectroscopy to enhance undergraduate chemistry classes. Dr. Asper, turn it over to you.
Great, thank you, Philip. So alkyl guanidines, it's actually a carbon with 3 nitrogen atoms. They're in a lot of different pharmaceuticals. So welcome everybody to Kitchen Chemistry Part 3. I feel like I have really big shoes to fill after the amazing talks that were given yesterday and the day before by my colleagues, Dr. Slunt and Dr. Giancarlo. So let's see how I do. Where's my slide work? So today's explorations, I'm borrowing a little bit from Dr. G, thinking about being in the kitchen, thinking about a meal. So our appetizer, we're going to do safety and a little bit of background. We're going to have a 3-course dinner, thinking about polymers in the chemistry. We're going to do some water pods, some shrinky-dinks, and some flour-based glue. And for dessert, we're going to have gum and chocolate. So safety-wise, and if there's one good thing that's come out of the pandemic, it's that now everybody knows what PPE is, personal protective equipment. That's what chemists think about when we think about our gloves, our goggles, and our lab coats. So our body protection, like Dr. Slund and Dr. G talked about, we usually use our lab coats. I'm using my apron because much like everybody else, my lab coat's still in my office. Our sense protection to protect how we make our observations. Sight, we usually wear goggles. Again, because we're here in the kitchen using kitchen items, I'm going to go with my prescription glasses. I'm just going to be very aware that I don't get what's on my hands into my eyes. The alumni are going to be like, Dr. G's not wearing goggles and yelling about goggles. Yeah, I know. It's okay. It's a pandemic. Smells, again, we're not going to have any big smells here, but remembering to waft, no big inhales. And touch, we would be using gloves, but here, since we're using all household items, our hands are going to be fine. We're just going to need to make sure we wash them thoroughly. Now, we usually would say don't taste, and that's actually something that we've said for the last 2 sessions, but today we're actually going to do some tasting, but we're going to be very careful and make sure that the chemical hygiene that we're going to be using is going to be the same as the kitchen hygiene that we would be using. Hi, William, steal my water. And make sure that we're cleaning our surfaces, washing our dishes, making sure that the tables are clean, washing our hands, doing all the things we do when we prepare food for eating. So remembering the definitions that Dr. Slunt and Dr. Slunt went over yesterday, I stole a lot of stuff. Polymers are large molecules composed of repeating structural units, typically connected by covalent bonds. And as those of you that did the experiments yesterday saw, there's natural proteins like DNA, and there's synthetic polymers like the Teflon tape, and some of the polymers that we'll see today. I'm going to talk to you again about polymers. And again, the important parts about polymers, they are made up of what are called monomers. Oh, no, my computer wants me to do something and I don't want to. So our monomers are individual units of our polymers. They can be then lumped together to make polymers. If the same monomer is repeated over and over, it's a homopolymer, and if it's different monomers, it's a heteropolymer. This one happens to be alternating. There's lots of other kinds. So let's dive into actually what we're going to do today. And our first one is going to be our biodegradable or edible water pods. Okay, computer, you are doing something on your own today. Uh-oh. Something's gone wacky. So hydration on the go is super messy. I know my kids always want a plastic water bottle when they're going somewhere. They would prefer a disposable water bottle to just about anything. But not only on the go, if you've ever watched a race and you see where the racers are given the cups of water at the water stations and they drink it and then they toss it down. Well, that's a lot of cups. And that's a lot of waste that has to be cleaned up. Now the race organizers do always go in and clean all this up. But what if all those cups were actually biodegradable and could be thrown in a compost pile rather than in a dumpster? Or even better, what if you could eat them? Kind of weird. Well, it actually turns out that there may be that product. It's already out there. It's a polymer called Ooho, and it's actually made by a company called Nopla, as in no plastic, or not plus, excuse me, not plastic. And Ooho is actually super cool because what it is it's a polymer that's made from algae, basically. And you can use it to encapsulate liquids or gels. So for example, in the upper sphere, you're seeing actually a water pod. And the idea is that you could be handed one of those while you're running. You could bite into it, suck the water out, and then throw that down because it'd be composted, or you could even just eat it. The lower packets, the red ones, those are actually ketchup packs. And it wasn't until I saw that it occurred to me how much trash we generate with our ketchup packs or the little peel back things at Chick-fil-A. That's a lot of garbage. What if you could somehow put ketchup in something biodegradable? And also the Nopla can be formulated differently and make takeout containers, again, that could be composted or even eaten. Too cool. So Ooho has actually been marketed as a biodegradable and edible water bottle. You can actually put other things in it too, like fruits and juices. In Europe, they actually are bringing a trailer to festivals and they're handing out samples and selling drinks in the Ooho pods, and people are biting in and slurping them up. And it's become really popular in Europe, and they're trying to get more investors and make it more available here in the US. Super fascinating. We can make something similar to Ooho in our kitchen. Now, we don't know exactly what they do to make Ooho because that's a trade secret. They don't want other people making it and making money off of their discoveries, but we're going to be able to use some very similar chemicals. One of the chemicals that we're going to use is something called sodium lactate, and I bought some, and it's a byproduct of fermentation of corn or beets. A lot of the corn that's grown in our country is fermented and then made and then used for ethanol and all kinds of other things. And one of the byproducts is sodium lactate. It's a white powder. You'll see it in a little bit, non-toxic. Sodium alginate is another polymer. This is actually another white powder that's non-toxic and edible, refined from seaweed. And you can use these for what's called gastronomical spherification. And there's actually a whole field out there called molecular gastronomy, where chefs are using the techniques of chemistry to try to enhance the dining experience. So you may have seen some things where people do drinks that have been frozen in liquid nitrogen and put them in their mouths and the vapors come out. There's 3D printing with chocolates and sugars to make foods, and there's actually this idea of gastronomical spherification, and very cool. And that's actually where these products were sold for. So if you're planning to eat your water pods, again, we don't usually eat in the lab, but since we're in the kitchen, it's okay. You want to make sure that, again, you do all those hygiene practices that you would do if you were making cookies. Wash your hands, thoroughly wash all your surfaces, your bowls, your spoons, and your blender with hot soapy water and rinse it really well. Okay, and I have let's see. So let's talk about how we're going to make our water pods, and I can go ahead and get started. Let me find my sodium alginate. Now, I'm not lucky and have a nice tall kitchen island, so I'm going to be doing a lot of jumping up and down in here. Now, I know that some people struggled to find the sodium alginate and calcium lactate, and they're not necessarily going to be able to play along. Uh-oh, my chemicals disappeared. Uh-oh. This is not good. All right, so what we're gonna do is imagine that I could find my pouch of sodium alginate, and I would measure out 1/4 teaspoon of the sodium alginate into cold water. I'd add some food coloring if I wanted to, and I'd mix it in the blender. And you're gonna mix it for 20 seconds, and you wanna make sure that it doesn't froth, okay? I discovered with a lot of trial and error in this kitchen that if the mixture froths up, you're gonna wind up getting bubbles that'll never break up and you don't get good pods, okay? Let me go ahead and change to my visualizer. Now, fortunately, I made some of this solution earlier.
Excuse me, how much cold water?
Thank you. It would be 1 cup of cold water. So it's 1/4 teaspoon of sodium alginate in 1 cup of cold water. And then you'll put it in your blender and you'll mix it for 20 seconds, okay? And when it comes out, it's kind of viscous and sticky, okay? It's thick. It's not, I guess it's not really sticky, but it's very thick. So I've made 2 of these here. I have a blue one and a purple one that I made earlier, just in case there was a disaster like this, okay? And you're gonna put your sodium alginate into a small bowl, a 1-quart bowl. So there's my purple. At the moment, are you seeing my bowl or my PowerPoint? Just out of nosiness.
Yes.
We are seeing your PowerPoint.
Oh, bummer poo. Let's see how we do this. Oh, that's what we do. Stop
Yeah.
here.
There you go.
There we go. I think now I've got it. Are we on my bowl now?
Yes.
Cool. Okay, I apologize for that. This switching thing is hard. So there is my sodium alginate dissolved in water. It's this thickish liquid. Now what we're gonna do is we're gonna do the calcium lactate part. And we're gonna use a bigger bowl. You'll want a 2 or 3-quart bowl. This one's a little bigger. And I'm gonna use 1 teaspoon of my calcium lactate. I really wonder where one of my kids put my phone. Interesting. So there's my 1 measuring teaspoon of my calcium lactate and 1 cup of cold water. And we're gonna stir it until it dissolves. Now, this next part where I'm gonna walk you through how to make the pods. This was definitely a trial and error thing. My Emma and I spent quite a while trying to get these pods to form well, and we learned a lot of wrong ways to do it and a lot of right ways to do it. If you're looking at the directions, or you've got the directions tell you to take a spoonful of the sodium alginate solution. So that's the thick colored solution that came out of the blender. And you're gonna lower it into, this bowl's a little small. You're gonna lower it into the calcium lactate, and you're gonna hold it for a count of 5. 1, 2, 3, 4, 5. Then I turn my spoon vertically and I slowly pull it out. And I wind up getting that little glob. Okay, let me do another one. Maybe I can turn my spoon.
Excuse me?
Yep.
How much sodium, calcium lactate, like how much do you add in?
It was 1 teaspoon in 1 cup of water.
Okay, thank you.
Like I said, this one may be really hard to play along because it is pretty intricate. This may be one that you're better off watching and then working on it on your own, because this one's a little tricky. Now, what's fun is trying different shapes and sizes of spoons. So for example, that was using a soup spoon. Here I'm using my teaspoon, and I've got some blue that I made earlier. I'm gonna put it in. 1, 2, 3, 4, 5. I'm gonna turn vertically and pull it out slowly. That one got a tail on it. That one looks more like a worm than a pod. Okay, you can make as many of these as you like. And the purple ones I think are easy. So let me make one more blue one. And what we're gonna then do is we're gonna leave this sit for about 20 minutes to give the spheres lots of time to form. 1, 2, 3, 4, 5, turn vertical, pulling it out. Oh, I'm making worms today. That's really strange. The purple seems to be behaving better. Again, experiments. The blue I made last night, the purple I made this morning. That may have something to do with it. And as you go, you may find that you get better spheres, or you may find that because you're nervous, they get worse. So there I've got 4 spheres and a couple worms. So we're gonna leave these guys for about 20 minutes so
Those
that
are cool.
they can finish polymerizing around the outside. We'll talk about a couple other experiments and then we'll come back to it and then I'll tell you how everything worked. Okay, so we're just gonna set that baby aside for a little bit. Let it do its thing. Not all chemistry is fast. And then we can go ahead and talk about our other experiments. All right. Next one's a fast one. I tried to intersperse fast ones and slow ones. This next one is making glue out of flour. Lots of recipes for this. You may have already done this in school. What I love about this particular recipe is it doesn't require any cooking. So what I developed this particular experiment for was for doing outreach activities. So maybe I'd be set up at a table at a shopping mall and kids would be walking by and getting to do experiments. And in that scenario, you don't want something that you have to cook. So let me get my stuff for that. Flour glue is super easy. You're going to use three or four teaspoons. Sorry, I gotta remind myself where I am here. Train of thought just went to the bus station. I'm gonna use 1 tablespoon of flour. My flour jar. And we're gonna put it in a Dixie cup like this. You can put it in any kind of cup you want. I like the Dixie cups because you can throw them away. Yeah, I know, I just told you that throwing away cups is bad. But again, because I was designing this to be used as an outreach activity, we wouldn't be able to clean hundreds of cups. So I'm gonna go ahead and put my tablespoon of flour into my cup. And then I'm gonna put in 3 to 4 teaspoons of water. Doesn't matter the temperature. I have my cold water left over from my previous experiment. 3 teaspoons tends to give you like school paste. 4 teaspoons tends to get you closer to Elmer's glue. So I've put 1 tablespoon of flour and 3 teaspoons of water and just spilled water on my laptop. This is not a good day. All right. Now what I'm gonna do, laptop anyway. All right. So now what I'm going to do is you could use a popsicle stick. I'm going to use the handle of my spoon and I'm going to stir up my glue. And mine is pretty pasty. Okay. Ew. Okay. So now what I like to do with this flour glue is I want to see how strong it is. And I want to prove to you that I can glue things together with flour and water. Looks like so I've got a couple strips of paper. And what I like to do with my flour glue is I'll spread a little bit on the end of this piece of paper. And I don't want to get too much on there because then it gets too wet. So I've got some glue on about this end of this paper. And now I'm going to overlap this piece of paper about that far. Okay, so what I've got here is a longer strip where about 1/4 of the 2 strips are overlapping, and I'm going to press it together. All right. If I try to pull on this right now, it'll probably pull apart because the glue's still wet. So we're going to give this about 3 minutes to dry. And while it's drying, I can talk to you a little bit about what really happened. and give everybody a little time to catch up. So what did I make when I made flour and water? Let me go back to my PowerPoint. So again, what did we do? In our small cup, we combined 1 tablespoon of flour with 3 to 4 teaspoons of water. How much water determines how much, how thin or thick your glue is going to be. With a popsicle stick, or I used the end of my spoon, I stirred it until it was mixed well. I spread it on paper and allowed it to set up. Okay. We're going to let it set up for those 3 minutes, and while we're doing that, we'll talk about what actually is happening on a molecular level. So what's happening? Well, let's think about flour. Flour comes from the seeds of the wheat, and what's inside the seeds of the wheat, inside of the endosperm, are these little vesicles that are containing the gluten. And what gluten is it's 2 proteins called gliadin and glutenin. And the gliadin and the glutenin are networked together to make the gluten. And it's water that helps cross-link those 2 polymers together. And when you get that gluten, gluten is sticky, okay? Unfortunately, a lot of people can't eat gluten, and that's really unfortunate because gluten is what makes really good bread so awesome. Think about a great baguette. You break open that crust and you chew it, and it's so chewy and wonderful inside. Or think about when you're kneading dough, that stretchiness. That's all coming out of the gluten, and it's coming from those molecules. So by taking flour and adding water, I was able to make gluten, and we know that gluten is gluey. And so we've actually made a glue. Okay. So let me test my glue real quick. Let's see which camera I'm on. All right, so I've got my paper. Now I'm going to try to pull it apart. Now I can't pull super hard or my paper will rip, which it just did because it was still wet right there. I don't know if you can see this, but the 2 papers are actually still glued together. And if my directions aren't going to be real good, but if I try to pull it apart this way, it will pull apart. But pulling side to side, I'm going to be able to see that they are glued together pretty well. And what's fun to do with this is maybe make some flour glue and use some Elmer's glue and glue up 2 pieces of paper the same way and test them and see which one's stronger. And don't just test it right now. Maybe wait a couple hours and test it. Maybe wait till tomorrow morning and test it and see which one of the glues is stronger. So here I've made a new one. I've spread it on, and I would just pull it apart this way. Now, right now this is pretty wet, so it might pull. Actually, it's already got some stickiness to it. So if you were stranded on a desert island, or you were social distancing and couldn't go to Walmart, you could make glue and do a craft. Anybody that's done paper mache, this is the kind of glue that you use when you're doing paper mache. So that's flour glue. I love this one. All right, let's see where we can go next. Next one are the kitchen shrinky-dinks. This particular experiment, this may be more of a listen along, because this experiment is going to be a story of real science and the fact that real science doesn't always work. So this experiment relies on using polystyrene, and most of us are pretty common with polystyrene in the upper form, styrofoam, or what's called expanded polystyrene. But it takes out, you can use that same polymer and make clear plastic containers like the one in the bottom right. Okay? You can also make clear hard containers like these fancy cups. Okay, these are great cups, not ones that were used to, red Solo cups are also made out of polystyrene. Okay, so what's neat about polystyrene is that you can use it in exactly the same way as commercial shrinky-dinks. What's a shrinky-dink? Well, a shrinky-dink is a product that you can buy at the craft store. I got a couple of them here. They're a thin piece of plastic film that you can draw on with permanent markers or with colored pencils, but usually permanent markers. And then you bake them in the oven and they shrink. and they become hard and rigid, and then you can turn them into keychains, Christmas ornaments, sun catchers, you name it. So what's really cool though is that this is polystyrene. So we should be able to go find some nice clear carryout containers and make shrinky-dinks. We'd be upcycling, that would be awesome. Except I never realized that most carryout containers are now polyethylene. And I've probably been nearly thrown out of 3 grocery stores over the past week because I'm going through the grocery stores, touching everything, turning them over, looking for the recycling code. And you're not supposed to be touching things unless they're buying them because of the germs, but I think I've touched every container at Walmart, Wegmans, and Giant, looking for polystyrene containers. And much like any of you probably experienced, I couldn't find any. But you know what? What I did find was some flat polystyrene. I found these really cool plates. Okay? So I decided I'm going to do shrinky-dinks with my plates. Now, why couldn't I find the darn containers? Well, it's actually super hard to recycle polystyrene because the majority of the polystyrene that's out there is the foam, and it blows out of recycling bins and creates litter. It's got a very, very high volume and a very low mass, so transporting it doesn't give you much product. It's just a nightmare to work with. It's also super contaminated. There's also not been a really big market for products using recycled polystyrene. Up until a few years ago, the only thing you really used recycled polystyrene for was to make Trex and some of those products. Now they're actually starting to use them to make coffee lids and silverware, but there's still just not enough market for as much polystyrene as we generate. And so since it's harder to recycle, fewer places are using it. So that's what. The other thing is polystyrene's really good for hot foods. And so where I usually see polystyrene containers like that is at the hot food parts of salad bars. There's no salad bars right now because we're in a pandemic. So when you're trying to do something in a classroom or a lab and it doesn't work, we call it a teachable moment. So let's have a teachable moment with our plate. So how do we do kitchen shrinky-dinks? Well, first you're gonna make sure you have your grown-up with you, have some oven mitts. You're gonna preheat your oven to 325 degrees Celsius. You're gonna cut your polystyrene containers into their desired shapes. You'll draw and color them in with permanent markers. You'll bake them for 10 to 12 minutes, and you'll remove them from an oven using oven mitts and allow them to cool. So I'm going to go ahead and switch over to my presenter camera and show you some of this. Some of this I did ahead of time just to make life easy. So a couple things that I made ahead that I'll show you. Oh, the other thing that I found that I could get a lot of to use were these little cups, okay? And our county's doing lunches for school-age kids, and we've been going and getting some lunches. My kids love getting to have their favorite things from the school cafeteria at home. And a lot of our vegetables and stuff came in these containers, and these were polystyrene. So that was awesome. So I went ahead and I cut out from my little dish, I cut out the shape I wanted. And in this case, I actually made a rectangle. Okay. And I drew on it with a marker, and I made 2 arrows on it. And this was the product of some experimenting. And these arrows are about the same length. The blue one's a little bit shorter. Okay. I put them on my baking pan, and covering your pan with some parchment paper or some aluminum foil is not a bad idea. It also helps with the fact that the grown-ups in your family are going, why are you putting plastic on my cookie sheets? Okay. So I've got that one there. And I actually went to the store when I couldn't find what I was looking for. I went to the store and I bought some commercial shrinky-dinks. So I've made a couple things out of that. My kids helped too. So these are from commercial shrinky-dinks. I made one shape. Oh, sorry about that. Got some commercial shrinky-dinks. I made one shape that is exactly the same size and shape as the polystyrene cup that I got from the school. We're going to bake that one in the oven. I've got a little heart that says chemistry. There's another little shrinky-dink. There's another one. So I'm going to tuck these into my oven at 325 degrees Celsius for about 10 minutes. All right. Now, while they're baking, I'm actually going to tell you some of the ending part of this story. So I put the plate in, and I was expecting to see that my plate, well, first of all, so here's one of those little rectangles. Let me go back to the other thing.
Dr. Asper, there's a very important question on the chat about should they ventilate their kitchen while doing this?
They do not need to. Polystyrene, and actually that's a good point. The only plastic you would want to do this would be polystyrene, recycling code 6. In particular, you don't, because this isn't going to make any smell, believe it or not. There is no outgassing, 10 to 12 minutes. There's no outgassing from this polymer, and that's why shrinky-dinks work. Do not do this with polyvinyl chloride PVC. You will outgas some chlorine and it'll be pretty bad. But I've been doing this for about 3 days and there hasn't been a single smell in my house. It's pretty amazing. Okay. So, like I said, I made those rectangles and I put those little arrows on them because I wanted to see how the shapes change. And I put them in my oven. And here's where my shrinky-dink came out. So what you can see is that it shrunk in both directions. So I had a long green arrow and a long blue arrow, and it shrunk, and the two arrows are now shrunk in about an equal amount, and I have this little hard rectangle. So cool. And then I looked at the piece I cut out of the cup, and I went, what? Because what you can see is that my polystyrene shrunk along the green arrow, but the direction of the blue arrow stayed long. It didn't shrink equally in both dimensions. And I'm like, I know. It's because my container was curved. So that's when I went to the store and I bought the plate. And I did the same trick. I put my two arrows that are about equal in length, and I put it in the oven, and I waited 10 to 12 minutes, and I got this. I got kind of a flower. It's all rippled, and there's like little holes in it, and I went, I know what's going on. If I look at this plate, it's got a flat part, and it's got an angled edge with all these scallops in it. So I bet it's the edge that's screwing it up. So I got out my handy dandy scissors and I cut around the edge and I cut the edge off. And I have one around here somewhere. So I cut all the edges off of a plate and I put it in the oven so it was just this flat part in the middle. And I put my arrows on and I baked it and I got this. It's a beautiful flower.
What?
Yeah. I think you could make this into a hair clip, personally. I think you could glue this onto a barrette and make the cutest hair clip on the planet. So it still didn't do the right thing. In fact, it doesn't look like it shrunk at all. The arrows are exactly the same length. You can't really see it, but everything's gone into this kind of flowery pattern. And I've done this 3 times. It happens every time. And I am like, what in the heck is going on here? So I did what Dr. G talked on Tuesday about having the scientific method and having a hypothesis. My hypothesis was that a plate would act like a shrinky-dink. Well, I have done an experiment and my results are completely bizarre. So it's time for me to go to the literature. And I did. So what was going on here is I had the molecule on the left, the little molecule, the hexagon with the, oops, hang on. Am I in the, nope, I'm not in the right place. Am I showing the right screen?
You're showing results now.
Okay. So My styrene polymer, the hexagon with the upside down V hanging off of it, that's actually what a styrene molecule looks like. And at each place where there's a corner on that structure, that's where there's a carbon atom. So when they polymerized the styrene and they made polystyrene, thousands of those all linked together and made the polymer that's shown on the other side with the brackets in the end. And that's saying that that particular set of atoms repeats over and over and over and over and over. So, but the shrinky-dinks worked fine. So it's not the polystyrene, it must be something else. Well, an interesting thing is that polymers and how they behave and what you're going to make doesn't just depend on the chemistry, it depends on how it's manufactured. And Jack Sellers, if you're out there, I'm going to make a hash of this. I apologize. Fix it in the chat window, please. All right, I'm going to make a long story short on processing polystyrene. When they make polystyrene, they actually make the polymer into these little plastic pellets, and they pour them into a big giant machine that does something called extrusion. And there's a screw that pushes the pellets through while it's heating them and slowly melts them and winds up coming out the other end. Think about squeezing a toothpaste tube. A shape comes out the other end. It might be a tube, it might be a solid cylinder, it might be a little sheet, maybe a thin sheet, it might be weird shapes. But that's the process of extrusion, and it makes the first processing of the polystyrene into this product that you're going to sell and do wonderful things with. But it's what they do next that's really wild. The next thing they do is something called extension. So you can imagine taking that cylinder out of the extruder and rolling it. Okay, so imagine you were playing with Play-Doh and you made the snake and then you rolled it with a roller. Well, what you would get then would be a sheet. And if you only roll it in the one direction, you get what's called an axial orientation. And what happens is that the polystyrene that you extruded stretches in one direction, and it's going to get thinner. However, if the machine you have on the other side pulls it from the opposite sides that it's rolling, so it's rolling out in one direction and it's being pulled perpendicularly, you're going to wind up getting a sheet that's wider and thinner. That's called a biaxial extension. And this is where the shrinky-dinks happen. Remember my arrows? Remember the shrinky-dink, the arrows shrunk in both directions? And the polystyrene cup, it only shrunk in one? Biaxial oriented polystyrene, axially oriented polystyrene. And I'm going to guess that this poor thing was probably somehow extended circularly. And so it contracted circularly when it was heated. How cool is this? I never knew so much about polystyrene. So polystyrene is what's known as a memory polymer, and there's lots of them, and they have all kinds of uses. They're actually used in yoga pants. This is why when you've worn your yoga pants for 6 or 7 days and they're starting to get kind of saggy, you wash them and you dry them and all of a sudden they look good again and you can wear them out of the house. Well, that's because the polymers that are in those yoga pants have a memory to them. And when you heated them up in the dryer, the polymer remembered that tighter, not the stretched out bit. Same thing happens with swimsuits. Okay. So what happens with polymers like polystyrene is that when they're processed, they've got that upper orientation of all their polymer chains in the red. But then when they go through that extension process, it changes the way the polymers are lined up. Think about Dr. Slunt's Teflon tape. You can see that blue polymer, they're all lined up, and the black dots are the crosslinks. Well, if you heat that polymer up again to the same temperature it was extruded, it goes back to the way it was. It remembers. The physics and everything behind this must be mind-boggling. But it remembers. So that's why the shrinky-dinks work. So when the shrinky-dinks were originally made, they were this size. Then the extension process made them into the thin sheets that we color on. But then when you bake it, it goes back the way it was. So if we're going to try to use shrinky-dinks from kitchen products, we've got to find biaxially oriented polystyrene. And I haven't found any yet. How cool is that? But like I said, I think this could be glued onto a barrette. I think this would be cool. All right. Where should we go now? Let's go back to our water bottle. switch back to my camera. How many of you have been kind of leaning in and looking at your water pods because you can't help yourself and you're wondering what they're doing? I made some the other day, so I know what they're doing, so I wasn't quite as antsy. Oh, and my shrinky-dinks are done. Hold that thought. All right, I'm putting on my oven mitt and taking my shrinky-dinks out of the oven. All right. So let's take a look at our water pods. Let me get my spoon. I'm going to use one of these plates. So I don't know if you can see this, but it's a round ball. It's a little bit squishy. Oh, I just dropped it. And it's a little sphere. I'm going to put it on the plate so it can dry. This one worked out pretty well. And remember, now it looks like a little bit maybe of my purple solution, my calcium, my sodium alginate may have not been sphericalized right away. That wasn't a word, sorry about that. There I've got another one.
Wow.
This one has a bleb. Look, it's having a baby. I don't know if you can see this, but some of the places where I just little drops fell off my spoon have made teeny tiny ones. Let's see how my worms look. Oh, okay, they held up. The longer you keep them sitting in this bath, the more rigid they'll be. I actually wanted to do some overnight, but unfortunately, my Emma is a little impatient and she kept taking them out and eating them last night. Okay, so, oh, that one looks like a worm. All right, so let's take a look at these guys. I need something.
Dr. Asper,
Yeah.
you have a couple of questions in the chat regarding your water pods. The first one is, could you flavor them?
You know what? Supposedly you can do this with fruit juice. And we tried it, but that was the batch that we had that the sodium alginate with the fruit juice got super frothy and I could not get the bubbles to break. And when I tried to do it in the calcium lactate, they just wouldn't form up. But I think you could absolutely flavor them. Like I said, I think you could experiment with this little experiment endlessly.
Okay, so then are they allowed to eat them?
If you practiced all that good kitchen hygiene that I talked about earlier, you absolutely can. And let me show you how to do that real quick. All right, so we did a lot of this at my house. So here's one of my, I'm gonna take the one that had the bleb. Now, if you really wanna do this the way that Ooho is gonna be used, what you're gonna wanna do is, again, bite into it with the front of your teeth and kind of suck in the water. All right, ready? That one went all the way in. Okay, so now what you might be able to see is that this one is all flat now. Oh, poopy, hang on, switch back. So this one's now all flat because I sucked the water out of it. So it looked like this before, and now it's all flat. And I can tell you, I did get a mouthful of food coloring to water. And if you want, you can eat them. Okay, so you can just take the flattened one and it's just kind of squishy. It has no flavor. Or if you want, you can take the water pod and you can just pop it in and eat it whole. An informal survey of the members of my household, ages 8, 4, and Fred doesn't want to talk about it. 2 of them found them tasty. 1 of them found them disgusting, and 1 of them said, no way I'm eating that, go away. So your family's experience may vary. The water tastes exactly like regular water. The color is just food coloring. And if it's juice, I think it will just take like juice. Again, that's the point of this. Remember, think about what that company's trying to, I mean, can you imagine being at King's Dominion? Oh, I'd kill to go to King's Dominion right now. But can you imagine going to King's Dominion and instead of having to carry around your cup all the time, you could buy this pod and just bite into it, suck out what you need, and then either eat it. And because I'm a mean grown up, I'd be like, oh, look, now I don't have to buy you an elephant ear. Eat your water pod. But you could then eat it, or you could they'd have a compost pile ready for it. Okay, so this thing's so cool. I love this. All right, so what was going on with the chemistry in our water pods? All right, oops. So the upper molecule is what sodium alginate is. So this is what came out of the seaweed. And when you process the seaweed, it's got a whole lot of sugar in it. That sugar makes up the cell walls of the plant. And that sugar, it's not glucose, so it doesn't taste sweet. It's a plant sugar, but it's completely edible. And so it is a long polymer. When we put it in the solution of calcium lactate, actually the only part of that we used was the calcium. And that's a calcium 2+ cation. It has a +2 charge. And what happened when I put them in contact with each other is that the sodium alginate has all these little sodium cations. When it came into contact with the calcium, those alginate strands got attached to the calcium. The calcium switched places with the sodium and made a cross-link. Go to yesterday's video with the paper clips. And that cross-linked polymer then, as it cross-linked and made a sheet of polymer, engulfed that water and made the spherical pod. Now you notice I had to be pretty tricky with how I did it to make the pod. And I am betting that the manufacturing on this is to die for. 10 years from now, I cannot wait to watch this on how it's made. Okay. So that's exactly what's happening, is we're just taking a polymer and we're cross-linking it, but we're doing it mechanically in such a way that it's coming around the water and capturing it and making these little spheres. Okay. From what I saw, and like I said, I didn't get to lead, I would be really interested to make a whole bunch of them, because you can put as many in a bowl as you can fit and take some out at 1 hour, at 2 hours, at 4 hours, at 6 hours. Some of them wait a couple days and see how rugged they'll get. So isn't this cool? I love it. All right.
Dr. Asper, one last question before you move on. How can they be disposed of? Down the drain or in the trash?
I would go within the trash, because this stuff is pretty thick and I can imagine it clogging. And I don't think anybody wants a grown-up unhappy with them with a clogged drain. The other thing I will warn you about, grown-ups watching, the sodium alginate is actually really clingy and hard to clean out of your blender. So when you clean your blender, reach in there with your hand and make sure you can feel that there's no gumminess left, because if there's any residual alginate in your blender, it will mold. Don't ask me how I know this. I thought it was clean. So then I had to bleach my blender. And you can actually see some of that gumminess on the spoon that you used when you pulled up. It'll feel a little gummy where some of that polymerization didn't go around. But and to be quite honest, another thing you could do if you have a good compost pile is you could go out and compost it and see how long it takes. One of the experiments I really wanted to do with you guys is I actually bought paper plates that were compostable, and I was going to see how long it took them to compost. But my compost pile is super young. It doesn't have all the right bacteria yet, and my plate's still completely intact. So again, teachable moment. Let's look at the shrinky-dinks before we get on to our closing. How am I doing on time, everybody? Or does anybody care? Is it like organic chemistry that you just never want it to stop? All right, so let me find my before pieces if I can. I get too much stuff out here. So you remember I had the piece of... Yep.
We're still looking at your PowerPoint thing.
Oh, please, hang on. Thank you. How are we doing now? Do you see my notebook?
Yeah.
Yay, thank you. I'll tell you what, teaching online this semester, I had a student who I swear his entire job was telling me when I had screwed up. So remember, when I cut this piece, it was about that tall. And here's the one that I just took out of the oven. So again, I replicated my experiment. My colors weren't consistent, bad experimental design. But what I saw again was that I shrank in this direction of the cup, but I did not shrink in this direction. So this tells me about how that particular polystyrene was processed. Okay, where's my other guy? I've lost somebody. Oh, here was where I took the identical size and shaped piece and I shrunk it with shrinky-dink, and you can see that it did shrink in both directions. And in fact, it maintained that parallelogram shape that it had, where this kind of curved because of the way it was processed. And then just to show you the crafty things you can do, You could see here where this one is now hard and it did shrink up. My little heart that said chemistry. What else did I make there? I made another one right there. So that's shrinky-dinks. If you want to do just the commercial shrinky-dinks, I picked my pack of them up at a craft store for $6. So you can absolutely do shrinky-dinks. You can put little holes in them. You can make jewelry. You can do all kinds of things. But again, we again showed ourselves that it's not just which polymer it is that makes a difference. It's how the polymer is processed. And that's why we need chemical engineers.
Dr. Asper, there was a question as to whether polyethyl terephthalate or PET could be used as a substitute for the polystyrene.
No, it doesn't shrink that way. It is not a memory polymer. And I think that one actually melts and just gets too gooey. And also with the polyethylene terephthalate, with some of the plasticizers and stuff that's in there, I think that could get stinky. Polypropylene doesn't work. I tried it. I didn't try any others because I didn't want to stink out my family. But polystyrene, and in doing a bunch of literature research, polystyrene was the only one I found that did this out of these. Now, as far as like really amazing synthetic polymers, there's tons of these. Dissolvable stitches are some of this. There's all kinds of medical devices that are memory polymers. So this is a huge.
Dr. Asper, could you use a hairdryer to go along with the directionality of the polymer?
I don't know. I'll try that next. Sounds like an experiment. Again, definitely use your grown-up. Some people use a toaster oven with these too, rather than using their big oven and heating it up. And when I've done this in outreach situations, we've used a toaster oven. And the thing is, we'd stopped doing this experiment at our big outreach workshops, and I didn't know why. And I think it's because we can't find the containers now that I think about it. So again, it's one of those, oh gee, I wonder why we haven't done that in years. Oh, now I know I can't find the containers. So I love the way I wanted to just make shrinky-dinks, and now I've learned all about polymer processing, recycling, why companies choose one polymer over the other. It's just opened up a can of worms. Are we ready for dessert? This is our easiest experiment of the day. All right, let's see, where am I? Gum and chocolate. So hopefully, if you couldn't find anything else, because I know this was a crazy list of supplies. You guys all thought I was a crazy woman, I know. Well, you need some chocolate. They don't even have to be kisses. I stole Easter candy when I was practicing. So what you're gonna wanna do is get a piece of gum, unwrap it, get a Hershey's Kiss, and unwrap it. Keep the foil, you're gonna need it. We're gonna take our piece of gum, we're gonna put it in our mouth, and we're gonna chew it with our mouths closed. Because if your family's like my family, I've seen so much chewing with mouths open since about the second week of March that I really want to die. Get it nice and that really good, yeah, I've chewed it enough and I'm ready to blow a good bubble consistency. Now we're gonna make the grown-ups cringe. Take the gum out of your mouth. If I had a dime for any time I tell everybody to put their gum back in their mouth. And take a look at it. Okay, looks like chewed up gum. All the grown-ups like, put it back in your mouth. All right, put it back in your mouth. Now you're gonna take a piece of chocolate and you're gonna put it in your mouth with your gum and you're gonna try to chew up the chocolate without swallowing everything. Eating chocolate makes me think I'm in Dr. G's office. Back at work. And while you're chewing it, pay attention how your gum feels. And maybe type in your chat window or give a quick shout out. How does your gum feel? Is this an improvement? I mean, I would think putting chocolate in anything would make it better. And once you got it chewed up, go ahead and take it out of your mouth. You might be able to see whether or not it looks a little different, but you can really feel it. So how's my chat box going? Is chocolate and gum an improvement? Are we going to get rich?
Well, we do have a question of what if you accidentally swallow the gum?
We'll talk about that in a minute. Just get another piece. We're gonna have some mortified grown-ups in a minute, I'm sorry.
You do have some mortified people. So you've got, this is disgusting, terrible.
My work here is finished. So what happened? By the way, if you don't like the gum anymore, go ahead and spit it out. It is pretty nasty. All right, I got in trouble for ruining a perfectly good piece of gum. All right, I really want another Hershey's Kiss, but I gotta talk. All right, so what is gum? Well, there's 4 components of gum. There's a gum base. It's called, also known as a resin. And originally, gum was made out of something called chicle. And chicle was the sap of rubber trees. And so it was just rubber. Now it's actually polyethylene. Easier to get at food quality, more consistency, all that good stuff. So it's just polyethylene. Okay. There's elastomers in it and wax that controls the different way that it feels. So some people like Trident, some people like Orbit, some people like Freedent. All those different feels that you get from the gum, or why bubble gum makes good bubbles, that has to do with the elastomers and the wax. And of course, there's the flavorings and the sweeteners. So if you if you accidentally swallowed the gum, or you intentionally swallowed it, like I used to do in high school when you would get caught with gum by the nun. I don't have gum. Polyethylene passes right through. So don't worry about it. It's gonna pass right on through. It's not gonna break down in your stomach. And I don't suggest you do like if you swallow jewelry and go look for it, but that's your experiment. I'm not going there. That would be biology. So what happened when we chewed up this gum with this chocolate? Well, we have to go back to what's the structure of the molecules. So whether we were chewing an old-time gum with latex rubber, or we were chewing new gum using polyethylene, what we see in both structures is that all we see is carbons and hydrogens. Lots and lots of carbons and hydrogens. That's all that's really there. What's in chocolate? Amazing, yummy goodness, stress relief, many, many things. But what's also in chocolate, and a Hershey's Kiss is a really good one to do this with, as opposed to a 97% dark chocolate cacao, the ones that your grown-up buys that are really gross and they buy them on purpose because they don't have to share. That chocolate doesn't work as well with this. Why? Because the difference is the amount of fat. There's a lot of fat in chocolate. There's cocoa butter, and there's what's known as butterfat. And this is an example of a molecule of butterfat. And again, if you look down that long chain of that zigzag, that's all carbons and hydrogens. So if our fat is mostly carbons and hydrogens, and our polyethylene is mostly carbons and hydrogens, they're alike. They have similar intermolecular forces. And we're back to Dr. G's vinegar-soaked kiss bears getting stuck together. So what happened when you chewed your gum with your chocolate is that all the fat and oil in the Hershey's Kiss, in the chocolate, was attracted to and stuck to your gum. That's why your gum got slimy, because all the oil was there. The sugars and the all that stuff from the chocolate went down the gullet, but the oil stuck to the gum, and that's what made it slimy. So you can have so much fun now. Siblings, annoying cousins, tell them, oh my God, I've got the yummiest thing ever. Chew gum and eat a piece of chocolate. You're going to have lots of fun with it. What'd we do today? We did a lot. We learned how to make a biodegradable polymer, and we actually saw that it can be used to capture water and maybe make the hydration vehicle of the future. We saw how polymers are processed, and the idea that the way that the polystyrene is processed after it's actually molecules made makes a big difference in its properties. We saw like dissolves like, and the alums that had me in chem may remember that intermolecular forces are everything. What do I want you to take out of general chemistry into organic? How to draw a Lewis structure? What are the intermolecular forces? Because I ask you about it constantly. And we learned a lot about how science doesn't always work and what scientists do when they get an unexpected outcome and they go make a bigger mess generally. Okay. So hopefully you've enjoyed it. I'm definitely gonna have Philip send out all the directions, because I know this was a little disjointed and fast moving, and some of these were pretty complex experiments, so I know you'll probably want to do them at a little slower pace. The other thing that's going to come out, I've got a reference list and also have my unit. Oh, but before I go, shameless product placement. I am on the American Chemical Society Committee on Community Activities, and our thing we do is we put together all the programming for 2 holidays every year, and you didn't know that these holidays existed, and they are such great holidays that they last a week. The first is National Chemistry Week, which is celebrated in October, and Chemists Celebrate Earth Week, which is celebrated in April. And what my committee pushes out twice a year without fail is a huge slate of activities that people can do in their homes, safety vetted. Like somebody said, well, do we have to vent the oven? No, because the American Chemical Society Committee on Chemical Safety vetted all my experiments before I even tried them, so I knew they were safe. So acs.org/outreach is where you can find all their stuff. The experiments that we did today came from Chemists Celebrate Earth Week 2020, Protecting Our Planet Through Chemistry. There's a lot of awesome activities here. There were amazing activities planned all over the world for Chemists Celebrate Earth Week, and then it had to all go digital because of the pandemic. One of the neatest things we do as a committee is we make this little magazine called Celebrating Chemistry. Hundreds of thousands of copies of this are distributed all over the world. And so there's one with every holiday. But what's also amazing is on the ACS website, there's actually an archive of the old Celebrating Chemistries. And so you can see, oh shoot, I put the NCWs twice. I meant to put the CCWs. So over the last couple days, when parents have been, grown-ups have been saying, you know, I'd really like to do more about this. I'd like to know about cooking. I'd like to know about this. There's probably a Celebrating Chemistry for it. And when I send out my references, there's going to be a link to this page. There's 3 categories of them, one set for National Chemistry Week, one set for Chemists Celebrate Earth Week, one set for International Year of the Periodic Table. And those are all, again, geared to be done at home with reasonably accessible supplies and done safely in the home. So shameless plug for my organization. And with that, we have any more questions?
Dr. Asper is wondering what molecule earrings you are wearing and what do you call them?
What you want to think about. If you want to think about these being all single bonds, this would be cyclohexane. If you want to think about these being alternating single and double bonds, this would be benzene. Good catch that maybe these big tacky earrings had something to do with what was going on.
So, question?
Dr. Asper, Julie Dendrilli wants to do yet another program. She's very into temperature and pressure, but this time she wants one with examples of styrofoam sent down to the bottom of the ocean and looking at temperature and pressure effects.
Styrofoam is really interesting because you're going to have a heck of a time sending it to the bottom of the ocean because it is, the density is so light. You know, if it's say, oh God, here I go with another inappropriate example. So say you think about all the movies about, you know, organized crime or whatever. What do they always do? They tie the body to a concrete brick and they throw them in throw them down with the fishes. You would never want to do that with styrofoam because you'd be caught right away because that body'd pop right up. Okay, that wasn't great. Sorry.
And Cheryl Kennedy shared that acrylic PMMA, polymethyl acrylate, shrinks at 100 Fahrenheit. But she's not sure about the off-gassing.
That's what I'm worried about.
And it does shrink in both directions.
Cool. Cool. Yeah, there's in the reference list I'm going to have, and this will be more of a grown-up, I found this amazing article talking about all the different memory polymers. I showed you a temperature one. There's some that are light. There's some that go with acidity. There's some that go with magnetic field. This is actually a huge area of research. This was just an easy peasy example of it, but it's a huge area of research. And actually the activities I showed you, the gum and chocolate and the edible water pods were actually out of Celebrating Chemistry and stuff that we've written for ACS. I didn't write the water pods. It's really cool. I actually wrote flour glue. The upcoming National Chemistry Week in October is going to be Stick to It, the chemistry of adhesives, because everybody likes glue and slime so much. We wanted to go with what else can you do with glue? And that's getting, and there's gonna be stuff in there about Post-it notes and tape. I don't know when that particular edition is going to drop. That'll probably drop in August, right before the national meeting. So if you keep an eye out on the acs.org/outreach, and all that programming drops like clockwork, usually August and March.
Okay, great. Well, thank you so much for doing this. We have had a great time this week with all of our chemistry faculty. I will say I'm a little biased, but I will say I feel like you'll not find a better chemistry department in any university our size anywhere in the country. So please, if this has interested you, think about where you're going to plan on going to school, and think about the chemistry department at University of Mary Washington. So once again, thank you all for joining us. Just as a reminder, everything has been recorded. It does take a few days for us to get everything uploaded to YouTube, but all 3 presentations will be put on the University of Mary Washington YouTube channel. And then I will be following up with an email tomorrow that will have the list of, or excuse me, the procedures for each of the experiments for all 3 sessions, as well as just a reminder of the link of the supplies that you would need. So thanks again to everyone for joining us, and have a great day.
Thank you. Thank you.